The graph shows the variation with time t of the velocity v of a ball from the moment it is thrown with a velocity of 26 meters per second vertically upwards. State the time at which the ball reaches its maximum height. Now at maximum height, the ball is instantaneously at rest. From the graph, v equals 0 at time t equal to 1.8 seconds. That's when the ball is at rest. State the feature of a velocity time graph that enables the acceleration to be determined. The acceleration at any instant in time can be determined from the gradient of the tangent line at that instant. Just after the ball leaves the thrower's hand, it has a downward acceleration of approximately 20 meters per second square. Explain how this is possible. Air resistance is present and acts on the ball just after it leaves the thrower's hand. The air resistance acts in the same direction as its weight and opposite to the direction of its velocity. The resultant downward force F is larger than the weight, so the weight and air resistance is a total resultant downward force. Hence, the downward acceleration given by F over m is greater than the acceleration of free fall. State the time at which acceleration is g. Explain why the acceleration has this value only at this particular time. At time t equals 1.8 seconds, the ball is at rest and air resistance is 0, hence only its weight acts on it. It therefore experiences an acceleration of g. Sketch an acceleration time graph for the motion. Show the value of g on the acceleration axis. Acceleration is given by the gradient to the tangent of the velocity time graph. So you can just calculate a few points to sketch a graph. So at time t 1.8, that's when the ball is at rest, and that's when the acceleration is minus 9.81 meter per second square. Explain why, for all real vertical throws, the time taken to reach the maximum height must be shorter than the time taken to return to the starting point. Now on its flight up, the drag force acting the ball is in the same direction as its weight. On its flight down, the drag force acting the ball is in opposite direction to its weight. Hence, the average acceleration on its flight up is greater than the average acceleration on its flight down. So A up is greater than A down. So using v squared minus vu squared equal to 2as, okay, this equation is valid for constant acceleration. So we end up with initial upward speed is 2a up times s, and then downward will be 2a down multiplied by s. So since a up is greater than a down, we end up with u up must be greater than v down. That's the speed. The final speed reached by the ball when it falls back onto the hand is smaller than the initial speed of projection. Hence, the average speed of the ball on its way up is greater than the average speed of the ball on its way down. Since the distance traveled up is same as the distance traveled down, the time taken to reach maximum height is less than the time taken to return to the starting point, because the average speed up is greater than average speed down. The ball starts with kinetic energy of 54 joules. Calculate the mass of the ball. So half mu squared equals 54, so u is 26, therefore m is 0.16 kg. Describe qualitatively how the amount of kinetic energy changes during the motion. The ball starts with initial kinetic energy of 54 joules. As it moves up, the kinetic energy is converted to gravitational potential energy and therefore reduces till it reaches 0 joules at the highest point. As it falls back, the kinetic energy increases as the gravitational potential energy is converted back to kinetic energy. However, as air resistance is present, the ball loses kinetic energy to the surrounding throughout its motion, and its final kinetic energy when it returns to its starting point will be less than 54 joules.